You know, when most of us picture the coast, we're probably imagining a peaceful beach, right? Maybe a quiet sunset. But this dramatic cliff collapse brilliantly illustrates that the coastline is definitely not just a static picture for a postcard. It's a powerful, active, and sometimes violently shifting natural engine. Okay, let's dive right into this.
Mastering A-level geography isn't just about memorizing textbook facts. It's really about understanding the raw, elemental mechanics of our world. So today, in this explainer, we're mapping out the coast as the ultimate dynamic system. We'll be looking at the exact inputs, flows, stores, and outputs you need to absolutely ace your exams.
Here's our roadmap for today. First, defining the coastal zone. Second, energy inputs and processes. Third, sediment stores and flows. Fourth, our high-energy case study at Nefyn Bay, and finally, our low-energy case study in the Maldives.
Part 1. Defining the coastal zone.
Let's lock down a piece of absolute must-know exam terminology, the littoral zone. Basically, this is the environment between the highest and lowest levels that the tides reach. Think of it as the ultimate active transition space, the exact arena where the sea, the land, and the atmosphere all collide and interact.
And because things are constantly crossing in and out of this littoral zone, we define the coast as an open system. What does that mean? Well, it's a system where both energy and materials move right across its boundaries. It's this continuous, flowing exchange. Honestly, once you start seeing the coast as an open system, everything else just clicks into place.
Part 2. Energy inputs and processes.
So, I gotta ask you directly, in a coastal landscape, where does the sheer, raw energy required to literally carve out cliffs and build up beaches actually come from? Take a second to think about it. Well, it comes down to three massive planetary-scale inputs. First up, solar energy. Thermal energy from the sun powers the water cycle and generates the winds, which in turn whip up our waves. Second, gravitational energy. The immense gravitational pull from the sun and the moon completely dictates our tides. And third, geothermal energy, from deep within the Earth. This powers tectonic activity, causing massive coastal uplift or submergence. These three are your ultimate coastal engines.
Part 3. Sediment, stores, and flows. All right, now that we're powered up, let's dive into the core academic mechanics. How does all that raw energy translate into moving physical earth and rock? Check out this idealized conceptual model of an open coastal system. Notice how clearly the boundary is defined here. Energy and sediment enter on the left as inputs, they get pushed through the system by processes, and eventually they exit as outputs.
Let's break that model down into a simple, four-step framework you can easily pull out for your exams. Step 1, inputs enter the boundary. This could be wave energy or maybe sediment falling from a weathering cliff. Step 2, processes or flows transport that material. A great example is longshore drift moving sand down a beach. Step 3, material enters stores. Basically, it gets deposited in a temporary sink, like a sand dune. And finally, Step 4, outputs leave the system entirely.
What's really fascinating here is how this cross-section takes that abstract block diagram we just saw and turns it into physical reality. If you trace the flows, those red arrows showing onshore and offshore transport, you can see them moving sediment between distinct stores. The backshore dunes, the foreshore beaches, the nearshore sandbanks, they are all interconnected sinks continuously trading material back and forth.
Part 4. Field tests, contrasting coasts. Now, theory is great, but A-level geography demands actual field evidence. It's time to put our system's knowledge to the test against real-world case studies operating at vastly different power levels. Just look at the extreme contrast here. On the left, we've got the destructive sheer physical power of a high-energy environment in Wales, completely dominated by mechanical erosion and mass movement. Then, over on the right, we have a low-energy environment in the Maldives, characterized by tranquil waters and constructive biological processes. Two coasts, two completely different open systems.
First up, high energy, Nefyn Bay.
We're focusing first on our high-energy case study to see an open system in sudden, violent motion. This is Nefyn Bay, a small coastal community on the Llyn Peninsula in North Wales. Back in April 2021, a massive slump developed into a terrifyingly fast-moving earth flow. It's just an incredible visual of mass movement. In fact, if you look really closely right in the middle of this earth flow, there is an entire garden bench just sitting perfectly upright. It's this surreal little marker riding a massive wave of displaced earth.
So the absolutely crucial point for your exam is understanding the mechanics of why this failed. The cliffs here are formed from unconsolidated glacial deposits, essentially loose, unpacked material left over from the last ice age. Interestingly, this wasn't even triggered by a massive storm. The weather had actually been dry prior to the slump. When it failed, it created a 100-meter, fast-moving earth flow straight across the beach. Notice how that instantly becomes a massive material input for the coastal system. It leads to high suspended sediment right at the wave base, where the sea is now actively eroding the toe of the landslide.
Part 5. Low energy, the Maldives.
All right, let's shift gears entirely. We're moving from the high-energy destruction in Wales to our low-energy case study, the Maldives. Here, we're looking at a fundamentally different set of inputs and stores. The Maldives is an archipelago of about 1,200 coral atoll islands right in the middle of the Indian Ocean. What makes this system so incredibly unique, and vulnerable quite frankly, is its elevation. The highest point in this entire nation is just 2.4 meters above sea level. Every single inch of this extensive coastal zone was built not by tectonic forces, but entirely by biology.
The inputs here are completely biological. It all starts with free-swimming coral larvae settling on a hard substrate. These larvae develop into polyps, which act like the microscopic architects of the reef by secreting a hard calcium carbonate skeleton. But this process has incredibly strict input requirements. It demands warm water, exactly between 23 and 29 degrees Celsius, and it requires shallow, crystal-clear water so sunlight can penetrate for photosynthesis. Under these perfect, pristine conditions, they grow, literally storing calcium carbonate as a physical landscape at a rate of 0.3 to 10 centimeters per year.
But as we know, human intervention inevitably alters natural systems. Just look at the capital city of Male. Because that tiny 2.4-meter maximum elevation makes them acutely vulnerable to rising sea levels and wave energy, the natural system has been heavily modified. What you're looking at is a $60 million artificial seawall, funded by the Japanese government, completely surrounding the city. It's a massive, hard engineering intervention designed to literally halt the natural flows of a low-energy system.
And that brings us to a final, absolutely critical question for your geographical studies. Whether it's a high-energy cliff in Wales facing stronger, more frequent storms, or a delicate coral atoll in the Maldives facing warming oceans and rising seas, how will climate change and our own extreme human interventions permanently alter these open systems in the future? These coasts are going to be forced to find a terrifying new balance. It's your job to understand exactly how. Keep exploring those systems, and I'll see you in the next explainer.